So inshallah in about less than a minute we'll start. Okay, welcome to the second lecture of E21. So in today's lecture, we're going to continue talking about what we've started last time, which was current and voltage. But before that, there's one announcement that I'd like to make. Due to the fact that some of you have classes immediately after this class. So the quizzes will be during the class time, and if we need extra time to cover the material, we'll do it outside the normal class time, and the attendance will be optional. However, I will record the video will be recorded for you to watch in your convenience. Okay, so if you recall from last time, we started talking about charges, and we stated that when we talk about charges, we're interested in two types or two possible behaviors. The first one is the force between two charges, whether they are of the same polarity or not. And the second thing is the movement of those charges. So the movement of those charges is corresponding to or related to the current. And the current is one of the key properties or key parameters of in this course and in every electric circuit. So current is defined as the rate of the electric charge flow. Whenever you see the word rate, it means derivative with respect to time, and that's what we have here. And it means that the more charges we have at specific time, the more current we have. And the current is actually the unit for the current is amperes, the unit for charge is coulombs, and the unit for time is seconds. So it's much easier. The problem with electricity in general is that it's not something physical, so you cannot sense it. You cannot see a current. You cannot see an electron that flows from one point in space to another. So it's always constructive to think about it in terms of something you are all familiar with. So the analogy that we usually have is when we talk about current, we're talking about water flowing. And it's usually water flows from the high altitude to the low altitude, or the high region to the low region. And in the case of high regions, the analogy to the high region here is actually the high voltage or the high potential. That was voltage. And the analogy to the low region is actually the low voltage. So that's the definition of the current, the rate of electric charge flow. The unit is amperes. And let's take an exercise here. We have two terminal. Yes, Yasser.
Doctor, in a circuit, isn't like the current flows always from the positive terminal of a battery? Doesn't that mean that it is flowing from the low potential to high potential of the battery?
We'll talk about it in a minute. So hold on to your question. This is a good question. Okay, any other question? Not other. So someone else was asking. Okay. Okay. Good. Okay. So let's take an exercise here, and in this exercise we have a two-terminal device. We'll talk about it in a couple of slides, especially when we talk about the ideal circuit element. So we have a current at t less than 0. There is no charge. No charge exists in the upper terminal here. So there is no charge for t less than 0. At t equals to 0, we start to have a current. We start to have a 5 ampere current that flows into the upper terminal here. So at t equals to 0 seconds, a 5 ampere current is starting to flow into the terminals. So what we are asked first is to derive the expression for the charge accumulating in the upper terminal of the element at t greater than 0. So think about it this way. You have at t equals to 0, you start a 5 ampere current is starting to flow into the upper terminal, terminal 1 here, of this device. And through as the time passes, you start to accumulate electric charges. Because remember, the current is the rate of flow of the rate of flow of the electric charges. So the question is, what will be the expression for the charges for t greater than 0? So as you expect here, at t, for example, equals to 1 second, the amount of charges that are flowing or accumulating at the upper terminal of this element will be greater than the amount of charges that are accumulating at t equals to half second, and so on and so forth. So let's start with the first part. So the equation that we have is the following. The current is the derivative of the charges with respect to time. So if we know the current, can we find the expression for the charges? What do you think? If this one is constant, please raise your hand. So the reason for that is I need to keep a record of who's participating. This one is 5 amperes. طيب محمد دخيل الله مهند دخيل الله.
It's gonna be Q, the charge equal the current time, the time.
Not exactly. This is good. Abdelkarim Basoud.
We need to derive them first.
What's
then
that?
We need to derive them first, then we can get them.
What do you mean by you need to derive them first?
Can I speak in Arabic just because it's
Yeah.
أحتاج كاملة أول بعد ما أجيب كامل.
Okay. You need to integrate it then.
Yeah, integrate.
Okay. Very good. Very good. Okay. That's exactly what you need to do. So you need to integrate this one from t equals to 0 to t ix dx plus the initial value here. So the initial value here is what? Aziz? Aziz, okay.
Yes, Dr. Abdul Hamidani.
Yes, Hamidani, yes.
Yes, Doctor. Can you show me the? I want to see the question first because I didn't read the whole question.
Okay, sure. because we need to. I will get back to you, disease. But we need to actually the slides are available on a Blackboard, so you may need to actually print them out and or have them in the Android device so you can refer to them. Okay.
Okay.
Omar, Sleh?
0.
Exactly. Why?
Because it's mentioned in the question.
Yes, exactly. So it mentioned that there is no charge exists at the upper terminal of the device. Okay, so this one is actually 0. So all what we need to do is to apply the integral now. It's going to be straightforward. The current is constant and it's equal to 5 amperes. So if we integrate, we will get 5t, and this is true for t greater than or equals to 0. So the second part is asking us if the current stopped after 10 seconds. So we were supplying the current for Shabab, please lower your hand unless you have a question. Okay, good. If the current is stopped after 10 seconds, how much charge has accumulated in the upper terminal? So we're supplying the current from t equals to 0 to t equals to 10 seconds. And then at t equals to 10 seconds, we stop supplying the current. So how much charges were accumulating? Hassan? Hassan?
It will be will depend on the first equation.
Yeah.
We will just plug in 10 in, and it will equals 50.
Okay, very good. Okay. So at t equals to 10 seconds, so Q10 will be 5 multiplied by 10, which is 50 coulombs. Exactly. So you see that it's straightforward application of the definition of the current. Now, let's talk more about current. So if you recall that here I mentioned that the current is the rate of electric charge flow, and it's something analogous to water flowing. But the reality is not that simple. The current is not flowing actually. The current is drifting. So if we talk about this circuit, and we select this portion and then we zoom in, then we see that the current is, if this is the electron will not just simply jump from this side to the other side. So the electron will push, or here, for example, this is a positive terminal, there will be positive charges. The positive charges will attract the electron in this atom, and this atom will be positive, so it will attract the nearby electron, and so on and so forth. The process will continue, and this process is called drifting. It's not flow. But for the sake of simplicity, and it's usually true in a sense that if we think about it from a simple point of view, from an analysis point of view, it makes our calculation, it makes our analysis much simpler. So we can approximate flowing of charges as water flowing. But remember, this is not the reality. The reality is current is not flowing, or electrons were not flowing. Electrons are drifting. Okay. Moving to the important point that the Aziz, I think, so Yasser, that Yasser has mentioned is that the current flow. What was your question, Yasser?
I said that the current always flows from the positive terminal of the battery. So I thought that the voltage goes
Okay.
from low voltage to high voltage.
Okay, very good. So the reality is, we're always saying that the reality is the negative charges that are the ones that move. So the positive charges will not move. This is the reality, but there was a convention and there is a misunderstanding long time ago that the positive charges are the one that are moving. So for that reason, the convention is actually the current is the direction of the flow of the positive charges and not the negative charges. So here, if we have this battery, then this direction is actually this is the direction of the flow of positive charges. And this one, let me use another color. So back to your question is, the assumption is that here we assume the direction of the current or is the same as the direction of the positive charges. So the positive charges will flow from this point, from the positive side of the battery, until they reach the negative side of the battery. Does that answer your question?
Yes, that makes sense. Thank you.
Very good. Any other question before we move? Yes, Ahmed.
Doctor, can I consider that the current is moving from the minus side, the negative side, into the positive side, and I put minus sign?
Where in the battery?
No, in the current.
What do you mean by the negative side and positive side?
The voltage, the battery, it's moving from the negative into
Yes.
the positive with the minus sign.
There's an internal process inside that, and there's kind of like electromotive forces and kind of potential that we it will be distracting to deep dive into. So I'd rather keep it as simple as this diagram and not to deep dive into it. But back to the question is actually, we assume that the current is flowing from the negative side of the battery to the positive side of the battery within the battery. So, and outside the battery is the other way around. But there's kind of like internal processes that I will avoid going deep dive into it because they're outside the scope of this course. But this is a good question.
Thanks.
Abdullah?
Doctor, is it in the drawing the currents, they're both going the same way? The orange and blue?
Oh, yeah, yes, exactly.
Okay.
Any other question? Okay, very good. Okay, Abdullah, can you lower your hand? Okay, now we're done with the current, so let's move to the second important parameter that we want to study. So second important quantity that we want to study is called the voltage, or sometimes it's called the potential difference. This happens when you have separation of charges. If you have separation of charges, then there will be a force between them, and this force will create an energy on any applied charge. So this leaves us with the definition of the voltage. So the voltage is energy per unit charge created by separation. So again, if you recall for the current, we're concerned about the what happens when we have charges that are moving. When we talk about voltage, what happens when we have charges that are separated in space. So in a mathematical way, the voltage is defined as the derivative of the energy, which is W, with respect to charges, dW by dQ. So V is the voltage, the unit is volt, Q is the charges in Coulomb, and W is the energy in joules. So you know that voltage is sometimes called the potential difference, and there is a reason for that. So it's much like the height of the building. So you can think about the voltage as kind of like potential energy. So let's take an example here. So if I assume that I have the following two buildings, and maybe one of you, hopefully not, is standing two buildings here. Two of you are standing here, not thinking about committing suicide. Okay. If I ask you if A and B have the same height, then what will be what will be the potential energy, or will A and B have the same potential energy? If this building, if this house and this one we call it like the cell phone tower. Okay, let me find Ali Talib.
Yes, to be the same voltage.
Okay, the same potential energy, and the voltage is exactly the same, because we can think about the voltage as kind of like potential energy. So to the resistance, if they are connected in parallel, if we have resistance 1, R1, and R2, and they are in parallel, it means that they have the same height. Think about it this way. It means that they have the same height. So if they have the same height, they should have the same potential difference. And the potential difference in our case is the voltage. Abdulaziz Al-Hamidani? Yes.
Yes, doctor. They will have the same potential energy if they have the same mass?
We're talking about not the object themselves, but as kind of like, let me call it this way, per mass. This will simplify the analysis.
So there is
for a unity mass, for example.
Okay.
Okay. Any other question? Right. Okay. So let's move on to the second portion of this lecture, and we're going to talk about an ideal basic circuit element. So it's very important that we emphasize that all the elements that we're dealing with, we're assuming that they are ideal. So this excludes all physical elements. So all physical elements, all elements that exist in nature, they are not ideal. I'm recording. Okay. Good. So all elements that exist in nature, that they are not ideal. So you may ask yourself, what will be? Yes, Ziad.
Are there ideal in real life?
No. But if we keep thinking about non-ideality when we analyze circuits, we need to account the analysis will be complicated, and you'll see that if you account for non-ideality, you will end up with not exactly, with the correct, for example, voltage or the current, with the correct voltage or the current with probably like 1 or 2% deviation from the actual value.
Okay, so it's for approximation.
Yes, exactly. It's approximation based. Okay. So you may ask yourself, what are the attributes of an ideal circuit element? So the ideal circuit element must have 2 terminals, which are the points of the connection for with other circuit elements. So we will not have a circuit element. And when you say like circuit element B, for example, a resistor, a voltage source, current source, voltage source, current source, capacitor, inductor. When we say like, usually we don't have it isolated. We have it connected to some other components of the circuit. So an ideal circuit element must have only 2 terminals, and those 2 terminals are the points where this circuit element is connected with the other or with the nearby circuit elements. So this is the first attribute. The second one is they can be described mathematically in terms of the voltage and or the current. So if you know the voltage and the current, you can describe, you can mathematically describe the circuit element. And the last important feature is actually they cannot be subdivided into other elements. So if you have a big circuit element and you keep subdividing into circuit elements, into sub-circuit elements, it means this is not an ideal, not basic circuit element. So a key word here is basic. Yes.
I did not get the first one. What does it mean by have only 2 terminals?
You may find, for example, not exactly in this course, but in other courses, if you are an E student, you will see that you will have an amplifier. And for amplifier, for example, you will have 3 connections, or maybe more than 3 connections. So, for example, here, if you have an op-amp, you may have 5 connections here, 5 points where you can connect circuit elements to this. So what we're stating here, this is not an ideal basic circuit element. This could be an ideal element, but not basic. So it means that we need to actually, in order to analyze it in this course, we need to subdivide it into ideal basic circuit elements. Does that make sense?
Yes, thank you.
Talal?
Yes, I didn't understand number 3.
You did not understand number 3. So number 3 is exactly similar to this one. This is what I was trying to explain. So if for example, this one, this could be the op-amp. And this one can be actually modeled into something like this. I forgot how it's modeled. I believe it's something like this. So you can see here that we kind of like divided it into sub elements. So this is a building block for a bigger circuit element. And if we dig deep into that element, we can divide it into, for example, a bunch of resistors, capacitors, and sources, for example. And that's the reason why we cannot think about this element as a basic circuit, ideal basic circuit element. We can think about it as an ideal circuit element, but not a basic, since we are trying to divide it. However, if we, for example, take another example here, if we take a resistor here, the resistor is an ideal basic circuit element. So you cannot divide it into, you cannot say that the resistor is equivalent to a smaller resistor plus a voltage source. You cannot say this is not an equivalent. You got the point?
Yes, thank you. I understand now.
Yes, Omar?
Doctor, so number 2 is just like capacitance or resistance, right?
No, number 2 is kind of like, it says that if you know the voltage, you know the current, you can easily model the relation between, you can easily model the elements. So all what you need to do, so sometimes you need to know the voltage, you need to know the current, and you need to know the nature of the element. So there are three important parameters: the current, the voltage, and the nature of the element. If it's an ideal basic circuit element, then if you know two of them, you can know the other. Shabab, okay, I need to move on. If you have any question, we can get back to it. Okay. For passive sign, since we're talking, if you recall that we're considering the movement of the positive or the negative charges, and this movement is kind of like giving us either like positive current or positive voltage drop or negative voltage drop. So whenever we analyze a circuit element, or whenever we analyze a circuit, we need to make a reference. So you cannot, this reference will help us actually differentiate or help us have a common ground among all of our analysis. And this reference is known in our case as the passive sign condition. What does it state? So this is the statement from the textbook. Whenever the reference direction for the current in an element in the direction of the reference voltage drop across that element, use positive sign any expression that relates to voltage to the current, otherwise use a negative sign. So this is kind of like confusing a little bit. So let me write it in a simple word. So in a simple word, if the current, which is I here, goes from the positive side of the voltage, or the positive terminal, of the voltage, then use the positive sign. for any relation between the voltage and current. So if the current here goes from the positive side of the voltage terminal, use the positive sign for any relation between the voltage and the current. Otherwise, use the negative sign. We'll see that, inshallah, in a few minutes, how this positive sign convention is going to play when we talk about the power, for example, and when we talk about the next lecture, we'll talk about Ohm's law, how this positive sign convention is going to affect our calculation. So for the time being, just take this statement. If I goes from the positive terminal of the voltage to the negative terminal, of course, then use the positive sign for any relation between the voltage and the current. So you see that when we talk about power, power is defined as the multiplication of the voltage with the current. Resistance is defined as the ratio of the voltage over the current. So we see that when we talk about power, that if the current goes from the positive side to the negative side, then we're going to use positive power. Otherwise, we're going to use negative power. So let's start talking about power here and see how to apply the positive or the passive sign convention. But before that, let me introduce. let me state the importance of power and energy. So usually, why we are concerned in power and energy? So most of the outputs of our electric systems are non-electrical. For example, if you have a motor, then the input is actually an electric energy. The output is a mechanical energy. If you have a heater, the input is electrical, the output is heat, etc. And most of the devices that we have, they have maximum power rating. So they have a maximum power that they can tolerate. As a side example here, if you're talking about waves that are communication signals that are transmitted from one point in space to another, from the cell tower to your phone, for example, you're not actually transferring voltage or current, you're transferring power. You're transferring energy from this point in space, from the cell tower to your phone. So that's why we always our understanding of like analyzing power and energy is very important. So the very first step in anything that we're going to study in this course is to define it. So what's the definition of the power? So power is the time rating of expanding or absorbing energy. So energy can be expanded, can be generated by the circuit element that we have, or it can be absorbed by the circuit element that we have. So the rate of change the time rate of expanding or generation of energy or absorption of energy is defined as the power. So mathematically, power is the derivative of energy with respect to time, or again, it's the voltage multiplied by the current. The unit is watts, and let's derive this one. Let's see why this one, the rate of change of energy, is equal to the voltage multiplied by the current. So if you recall, the voltage is defined as the derivative of energy with respect to charges. The current is defined as the derivative of charges with respect to time. And this one is V, this one is I. This will cancel with this, and you will end up with okay, any question here? Yes, Hadi.
Doctor, is this mathematically correct that we just simply cancel dq with dq?
Yes.
All right, thank you.
Okay, good. So now let's see how passive sign convention is going to play here. So the power could be positive or could be negative. If the power is positive, what does it tell us? So it tells us that the element that we have is going to dissipate power or dissipate energy, meaning that the power is being delivered to that element. As an example, for example, here, so resistors usually consume energy. Think about resistor. Take an example of a well-known resistor is the light bulb. So you're supplying energy to the light bulb. So the power is going to be positive here because the light bulb is actually taking this energy and dissipating this energy. So the power is positive in this case. The power could be negative if the power is being extracted from the circuit, or the power is being generated by the circuit element. As an example here, sources. If you have a battery, for example, the battery is supplying energy to any circuit element that's usually connected to. So sources generate energy or generate power. Yes, Abdullah. Abdullah Bajani.
Abdullah. So do you mean, doctor, that the power and voltages in batteries, is negative?
Most of them. There's some occasions when the power is actually positive. I think about it as if you are لما تعطي اشتراك السيارة. So
okay. Thank you.
واحدة من السيارات تكون positive اللي هي طافية، اللي شغالة تكون negative. So you're connecting one battery to another. One of them is positive, which is the one that's being supplied to, and the one is negative, which is the one that's supplying.
Okay.
Okay, now let's see how passive sign convention is going to be used here. So the relation between the voltage and the current here is in terms of power. So P equals to V multiplied by I. So let's think about the sign here. Will it be positive or negative? So let's take, for example, this one, A. So remember, for the passive sign convention, the current is entering from the positive side of the positive terminal of the voltage. So the power here should be positive or negative. The sign here will it be positive or negative? Karim, yes.
Positive.
Positive, exactly. What about this one? Munir?
It's negative.
It's negative. Why?
It's جالسة تدخل على الموجب مش جالسة تطلع منه.
Okay.
جاية تجي من الديفايس.
Okay, very good. What about this one? Let me see. I'm looking for new names. طيب من الطلعة لكن الله ياسر بن عمر عبد الله اليوسف أو عبد الله اليوسف.
Because it's going to the positive terminal from the negative one, so it will be negative.
Okay, very good. Exactly. Sire, what about D?
It will be negative.
D is negative?
Oh, negative and negative will be positive.
D will be positive. Why?
It is negative and going in the opposite direction.
So it's entering here. Think about it this way. It's entering from the positive. So, okay, very good. Any question here? So let me ask you this question. Do you think whether you use this convention, A, B, C, or D, do you think the value and the sign of the actual power, do you think it will change or it will stay as it is? Khalid?
It will stay as it is.
Exactly. Because all of these are kind of like assumptions. So you assume that the current is flowing this way and the voltage drop is this way. And based on your assumption, you should reach to exactly the same conclusion. So it doesn't matter what will be as long as you're consistent, it doesn't matter what will be the start, what the starting point would be, you will end up with the same with the same results. Okay, very good. Any question before we proceed? Let's take an example and see how this is going to be how to apply the passive sign coefficient. Okay, very good. Karim, question? Okay, good. Right. So here, what we have, we're assuming that we have 20 voltage drop across the elements from terminal 2 to terminal 1. And the current of 4 amperes enters terminal 2. So if we think about it this way, this is the so what we're saying here, that the voltage drop is from terminal 2 to terminal 1. So terminal 2 has higher potential. So terminal 2 should be the positive one. And the current is entering from terminal 2. So this is the direction of the current. Now, let's specify the value of the voltage and the current using all of these polarity references here. So we can use A, B, C, and D. And let's see what will be the voltage, what will be the current, and what will be the power. Okay, so let's start with 1. So who can help me with this one? So what I want you to do is I want you to find the voltage, the current, along with their signs, and the power. So the power here is going to be positive, V multiplied by I, because this is the direction that you assume. I need a new one. كلكم عزيز مرة صغير. Okay. So all of you have participated. So let me start with Ziad.
Yes.
Go ahead, Ziad. So what will be the voltage here? Again, the voltage is 20.
20 drops from 2 to 1.
Yes, so according to this figure, what will be the value of the voltage?
Is it double? Because
no, it's going to be negative, right?
Okay.
Why is it negative? Because we're saying
it
yes.
enters the positive.
Yes, because we're saying that the voltage drops from terminal 2 to terminal 1. But according to this reference that we have, the voltage is dropping from terminal 1 to 2. So this is just a reference. This is a fact here. So we know for sure that the voltage drop across an element from terminal 2 to terminal 1, and the current enters from terminal 2. This is, let me write it down here. This is a fact. Those are references, or let me call it assumptions. Okay, is it clear, Shabab?
Yes.
الدكتور ما فهمت ممكن تعيد؟
What we're stating here that the fact is actually the voltage. There's a 20-volt voltage drop from terminal 2 to terminal 1. It means that terminal 2 has a higher potential compared to terminal 1. Is it clear now? Is it clear this way? Okay. Yes. And the current is entering, the value of the current is 4 ampere, and the current is entering from terminal 2. Those are the two statements are facts. And we can make any assumption of the circuit element that we have in terms of references, in terms of polarity references. So A, B, C, and D are kind of like assumptions. So, for example, in A, we assume that the voltage is actually terminal 1 has higher potential than terminal 2, and the current is entering from terminal 1. This is our assumption.
Yes.
Okay.
Yeah, you mean based on those assumptions?
Yes.
Our light, is it negative or positive?
Exactly.
Yeah.
So, for example, B, or for example, A here, the voltage, according to this assumption, is terminal 1 has higher potential than terminal 2. According to this assumption, terminal 1 has higher potential compared to terminal 2, but this is not the fact. The fact is the opposite, right? Terminal 2 has higher potential than terminal
1. So it's reversed.
It's negative.
Yeah.
So the negative sign here tells us that the voltage drop is opposite to what we have here.
Okay, thanks.
So now let's go with the current. Who can help me? Let me look for a new name. Mahsen?
Yes, will be -4.
It will be exactly -4. Why?
Because it is go from the negative to the positive.
Yes, exactly. So power here, again, this is the convention. So according to this reference, the power will be positive, right? The current is flowing from the positive terminal of the voltage to the negative terminal of the voltage. So P will be V multiplied by I. V is -20, I is -4, and the product is 81. Okay, let's.
Doctor,
Yes.
can you explain why the current is negative?
Okay. According to the fact that we have, the current is flowing from terminal 2 to terminal 1, صح?
Yes.
This is a fact.
Okay.
Why? Okay. It's clear?
Yes. Because the reference was distracting because there is an error for the current.
Okay. The current here, according to the reference or according to the assumption, is flowing from terminal 1 to terminal 2. That's why we have. Okay. So who can help me with the second one? Let me look for another name. Okay. Khalid Hassan. Participated. Adnan?
Yes. Can you please go to the previous slide?
Yes.
So the voltage will be negative.
The voltage will be negative. Okay. Why, Adnan?
It's just same as A.
Yes.
It is, yeah.
Exactly. What about the current? I need some Walid. Walid Aqil.
Yes, the current is 4 ampere.
The current is positive, صح?
Positive, yes.
Why positive?
Because at the same sign.
Okay. So according to the fact, the current is entering from terminal 2. And according to this reference point, or this assumption, is the current agrees with the fact, right?
Yes.
So the power, again here, is according to the passive sign convention, is negative, the product. Is it clear why the current is negative? I'm sorry, is it clear why we have a negative sign here? If it's not clear, please ask.
Yes, doctor. For the voltage, why it's negative now?
Why is negative? Let me ask you this question. Why the voltage is negative? Who can help? من اللي سأل؟
عبد العزيز.
عبد العزيز الحميداني. Okay. Who can answer عبد العزيز question? Okay, Omar.
Because it's the opposite of the fact mentioned in the question.
Okay, Abdulaziz. So the question is telling you that the current is entering, or the voltage drop from point, the voltage drop from terminal 2 to terminal 1. So terminal 2 has higher potential compared to terminal 1. And according to this assumption, you're saying that, or the assumption is stating that terminal 1 has higher potential compared to terminal 2.
Okay, now it's clear. Yes.
So the negative sign here is because of the passive sign convention. If you remember the passive sign convention, we use a negative sign. We use a positive sign if the current is entering from the positive terminal of the voltage. Here, the current is actually entering from the negative terminal of the voltage. So that's why we have a negative sign. So negative multiplied by 20 multiplied by 4 is going to be 80 watts. As you can see here, as long as we have the same facts, so the fact does not change here. Any reference point, any reference polarity that we're going to use, we're going to end up with the same value of the power. Okay, is it clear, Shabab?
Yes, Doctor.
Okay, so I need to stop here, and I will post the solution for the remaining parts of this question, and inshallah from next class we're going to solve the remaining two exercises on the board, and I will we'll start chapter 2. Okay. I'll be sticking around if you have any questions.